Okay, with that, we can close the chapter of variational autoencoders and move on to unconditional GANs. Most of these slides I covered last year, so I'm not going to be spending too much time on unconditional GANs. I think there is going to be only one new slide towards the end. So this is going to have a review flavor for a while. And then we are going to go through it really fast, and then you can stop me to ask questions. The video is online. You should definitely watch it. But what is the big picture of generative adversarial networks? The big picture is, unlike variational autoencoders and unlike what we have been doing so far, you want to get rid of the likelihood. You don't want to keep maximizing your likelihood. Is there an alternative to the maximization or maximizing the likelihood paradigm? And why would you do that? Because when you are writing your marginal likelihood, and when you are doing variational autoencoders, your marginal likelihood, you didn't have a closed form formulation for it when it came to generating images. And rather than maximizing the likelihood itself, you were maximizing a lower bound on your likelihood. And then you were making some assumptions, some normality assumptions, which may or may not be good assumptions. And that was a bottleneck to the quality of the images that you're going to get in the end, the quality of the generated images. So you want to have an alternative to maximum likelihood estimation framework. And that alternative is based on this observation that we are really good at solving discriminative tasks. We are really good at solving classification tasks. And we had the most success doing that using deep learning. And actually, we were reframing many of our problems and classes of problems into classification. And then we were solving them using neural networks. We are really good at that. Can the loss function for our generative process, our generator, come from a discriminator? And the answer is yes. And what you're doing now is, and all you're doing is comparing real data to data generated by your generator. And then you're going to ask a discriminator to distinguish between the two. But there is a catch here. Your loss function, unlike before, you don't know its functional form, or perhaps you know its functional form, but it's going to look really complex. Why is it complex? Because the loss function on its own is a deep neural network. Your discriminator is actually a deep neural network on its own, and your generator is another deep neural network. And based on the fact that there is no free lunch, yes, you got rid of your likelihood, and you got rid of maximum likelihood estimation framework. Perfect. You wrote down an objective function using a discriminator, but there's a catch. Optimizing this is going to end up being a nightmare. So you're going to have a lot of trouble getting generative neural networks to converge. And there's going to be a lot of literature on trying to modify your objective function and try to regularize your neural network, try to come up with better architectures. And that's exactly why we have so many slides on GANs. The big idea is clear, but the details, once you sit behind a computer, you need to know a lot of tricks to make them converge. It's the same thing with reinforcement learning. The big picture is clear, but there is a lot of hyperparameters that you need to tune to make them converge. And if you start with this simple objective function, there is actually math behind it. It's not like you're simply distinguishing between real and fake. Behind the scenes and mathematically, this framework is working because in the end of the day, your objective function is going to end up being in the form of a distance between two distributions. And that's the Jensen-Shannon divergence, which is going to come out of KL divergence. So you're trying to minimize the distance between your probability distribution over the data and the probability distribution over the generated images. But there is a catch here. If you knew the functional form of your P, then you would be fine. You would just write down your Jensen-Shannon divergence or any other divergence. So this is not going to give you your objective function. Your discriminator is going to give you the equivalent objective function. Why is that? Because these are complex underlying distribution over the space of images. Writing a closed form or approximate probability distribution over them is going to end up being really hard. But perhaps you can sample from that or sample similar looking data from that complex underlying distribution. So that's the idea. You are giving up something. You are giving up the luxury of having a closed form solution on your probability distribution. So GANs is not going to give you a probability distribution. It's just going to give you the mechanism to sample from that distribution. And what is that mechanism? You sample from a simple distribution, push it through a complex nonlinear function, and then that's going to give you complex looking samples. And then the idea is, and the entire trouble is trying to train G. And your discriminator's job is just to give you the means of training G. And that's all I want you to take home from this slide. In the end of the day, you are interested in G, and the discriminator is just there to help you train G. So another neural network is helping another neural network to train. That's the big picture behind GANs. And in the next few slides, we are actually going to a lot of details of why this is not the best objective function to work with, how can you improve upon it, and if you improve upon it, what type of divergence are you minimizing, what is going to change, how are you going to put restrictions on your discriminator, on your generator, modify their architecture so that they converge better. And we are going to cover a lot of details. And at the same time, if you have a generator generating some images, how can you compare one image to another one? How can you compare the goodness of two generated images? What is your evaluation metric? And these things we are going to keep covering. I think it's a good time for me to stop